Challenge. The challenge is to analyze what happens from the moment a person doing bungee jumping launches until they reach the lowest point. For this challenge, we divide into two phases. The first one is to analyze of what happens from the launch until the rope reaches its natural length, just before the stretching of the rope begins due to the effect of the person's weight. And the phase two, to analyze what happens from the moment the rope reaches its natural length and begins to elongate, until the person reaches the lowest point.
So for this part of the model, I'm gonna explain what happens when the person walks into the void with an initial velocity of 0 and with an initial position of also 0 meters. Since we are ignoring air resistance in this model, the only force acting on this person as of now is the force of gravity, which is the mass times the gravitational acceleration g. And notice that the rope is not exerting any forces now because it is not completely stretched. Using Newton's second law of motion, we know that the sum of the forces equals mass times acceleration. And since the only force acting on this person is m times g, we can define our differential equation to be the mass times the acceleration, which we'll define as the second derivative of the position. Notice that both sides of the equation contain and since we know for a fact that the mass of the person cannot be 0, we can safely divide both sides and get our differential equation y double prime equals just the gravitational acceleration g. And starting from this, we can get an equation, a function of the velocity, which is just going to be the integral of the acceleration, which is g, with respect to time. And by the same means, we can get a function for our position, which is just going to be the integral of the velocity with respect to time. Using these three functions, we can calculate the time that it will take the person to reach the maximum, the maximum height before the rope starts to stretch. We can just solve for the position. We can just solve for t, and using this value, we can substitute it in the velocity function to know what will be the final velocity at this time.
So for the second part of the case study, in which the jumper already reached the total length of the rope, we can model the system using Hooke's law, which states that the force exerted by a spring is proportional to the displacement from its equilibrium position. Here, K is equal to the spring constant, and delta X is equal to the displacement of equilibrium. Now, if we apply Newton's second law, which states that the force is equal to mass times acceleration, where acceleration is the second derivative of velocity, we can say that the only forces acting now are the spring's restoring force and the person's weight. Therefore, we're going to get the second-order homogeneous differential equation. If we find the characteristic equation and then general solution, we can describe the harmonic motion of the system.
Now that we have our differential equation, we can find its general solution by substituting it into a quadratic equation and then finding its roots. For simplicity, we will also take the square root of the quotient between the spring constant and the mass as W sub 0, and therefore our equation for position would be the following, and taking its derivative would give us its velocity. Now, substituting for the conditions in our system, where we have a spring constant K of 15 newtons per meter and a mass for this person M being of 60 kilograms, we would end up with this final equation for position and for velocity. If we graph these equations, we can find its position of first maximum on 28 times the square root of 7 when pi seconds have passed. And we can also observe how the velocity on this orange line decreases as time goes and reaches 0 when the rope has achieved its full stretch length, giving us a total height of about 70 starting meters plus our maximum stretch being roughly equal to 107 meters, and a total time of almost 7 seconds for the duration of all this scary experience.
In conclusion, this case study demonstrates how differential equations effectively model natural phenomena, as seen in examples like freefall and oscillatory motion. In phase 1, Newton's law helped predict the jumper's acceleration and time to reach a certain distance and velocity under gravity. In phase 2, after reaching the full length of the rope, the jumper experiences elastic motion, behaving like a spring. Thus, differential equations are useful for making key calculations to ensure safety in real-world applications.